Hello and welcome. Up to this point in the class, we've been addressing relatively simple research questions. This week we're going to broaden our horizons a bit and talk about analyzing numerical variables when our research questions are a bit more complicated, starting with the analysis of something called paired data. It shouldn't surprise you that we're going to start our discussion with an example. Here we're looking at data on test scores. These are 200 observations randomly sampled from a survey called High School and Beyond. And the same students in this survey took a reading test and a writing test. The box plot below shows the distribution of those scores. So we want to know whether there is a difference between the average reading test score and the average writing test score. So looking at the plot below, at first glance, does there seem to be a difference between these scores? Well, we can see that the median for the writing scores is higher than the median for the reading scores, and the spread of the writing scores is a little bit smaller than that for the reading scores. So the reading scores are more dispersed. So the real question that we want to answer is whether that difference is statistically significant or whether we think that it is just due to random noise. So here we have sort of an abbreviated look at what this data would actually look like in a data set. So we have 4 columns in this data set. To the far left is just a counter up from observation 1 to observation 200. Just to the right of that is an ID. This is a unique identifier assigned to each of the students in this sample. So we don't attach the students' names to their test scores, we just give them a unique identifier. And then we have a column for the reading test scores and a column for the writing test scores for each of those students. An important question to consider is whether the reading test and writing test variables, those scores, are independent for each student. Take a minute and think about that before we move on. The answer is no, that for each individual student, the reading score and the writing score that that student got are not independent of each other. So that is to say that how well a student reads and how well a student writes are related to each other. How well a student reads and how well a student writes is associated with the student's underlying ability and facility with language, as well as other things like how comfortable that student is in the test-taking environment, or whether the language the test is administered in is the student's native language, things like that. So the reading and writing scores are associated, they're dependent on one another, not independent. When our sets of observations have this special relationship to one another, where they're dependent on one another, they're said to be paired. So this is the paired data that is the subject of this lecture. When we analyze paired data, frequently it's useful to look at the difference in outcomes in each of the pairs of observations that we have. So we might want to know, for example, what the difference between the reading and writing test scores are for each student in our sample. And of course, when we create this new variable, the difference variable, we need to subtract using a consistent order. So always take read minus write, or always take write minus read, but don't switch those up as we take the difference between those variables. So here's what this data would look like. We have the new difference variable off to the right. The first entry in that difference column is 5, which is the reading score 57 minus the writing score 52 for observation 1. So 57 minus 52 is equal to 5, and we're going to do that for each of our 200 observations. To the right of this data table is a plot of the difference in scores for our students. Remember, we started out by asking whether there was a meaningful difference in the reading scores and the writing scores for the students in our sample. So our parameter of interest is the average difference between reading and writing scores for all of the high school students in the population that we're interested in. The point estimate that we have is the average difference between reading and writing scores in our sample, so the average difference among the 200 high school students that we sampled out of this survey. So we want to know whether there's a meaningful difference between the reading and writing scores. If there is no difference between the scores, what would you expect the average difference to be in this difference variable that we're looking at? And then given that information, what are the hypotheses that we would use to test whether there actually is a difference between the average reading and writing scores? Take a minute and pause the video and think about that. So if there is no difference between these two scores, then the average of the difference variable in our sample should be 0. And our hypotheses are the null hypothesis, that there is no difference between the average reading and writing score, so that the mean of the difference variable in the population is 0. And the alternative hypothesis is just that that mean is not equal to 0, that there is a meaningful difference between the reading and writing scores. So we started out by looking at data on two different variables, the data for the reading test scores and for the writing test scores. But even though we started out with that data on two variables, we're going to end up doing analysis that's just the same as what we've been doing before, because we collapsed those reading and writing data into one variable that captures the difference between those scores. And we're just going to be testing to see if the average difference, so the average of that variable, is meaningfully different from 0. So you know the hypothesis testing drill by now. We need information on the mean and standard deviation of the variable that we're looking at. So the mean of the difference variable is negative 0.545, and the standard deviation of the difference variable is 8.887. So we're going to use that information, and we're going to calculate our z-test statistic and then find the associated p-value for that test statistic. One thing to keep in mind is that we're doing a two-tailed hypothesis test. Our alternative hypothesis was that the difference is not equal to 0, so that could mean that the difference is greater than 0 or less than 0. It's not a directional hypothesis test, it's a two-tailed one. So let's calculate our z-test statistic here. We're going to take the observed mean minus the hypothesized mean under the null hypothesis. So our observed mean is negative 0.545, and under the null hypothesis, we say that the mean of the difference variable is 0, that there's no difference between the reading and writing test scores. So that's in the numerator. In the denominator, we need the standard error. Now remember, we take the standard deviation and transform it to get the standard error by taking the standard deviation divided by the square root of n. So n is 200, so in the denominator we have 8.887, the standard deviation, divided by the square root of 200. That's the square root of n. When we work that out, we get negative 0.545 divided by 0.628, which gives us a z-score of negative 0.87. We can look that up in a z-table. The z-table is going to tell us that the area under the curve to the left of that point in the standard normal curve the z-table is showing us is 0.192. And we need to multiply that by 2 to capture the area under the curve less than negative 0.545 and greater than positive 0.545 because of our two-tailed hypothesis test. So 0.192 times 2 is 0.384. So 38.4% of the area under the curve is more extreme than this value of positive or negative 0.545. And remember, to reject the null hypothesis, we're looking for a p-value of less than a particular cutoff. In this case, we're going to use this cutoff of 0.05. So the p-value that we found is 0.384, which is substantially greater than 0.05. So we're going to fail to reject the null hypothesis. So we're sticking with the null hypothesis as our best explanation of the data that we observe. So we don't have convincing evidence that there's a difference between the average reading and writing test scores. So here's a good opportunity to test yourself and see if you remember what a p-value actually means. Take a look through these options and see if you can remember which is the correct interpretation of a p-value. And the answer is that a p-value in this case is the probability of observing a difference in scores at least this large if in fact the null hypothesis is true. The average difference really is 0. So we observed a p-value of 0.384, which means that if the null hypothesis is true, we have a 38.4% chance of observing a difference as extreme or more extreme than we observed. So a 38.4% chance is pretty substantial, so we don't have good evidence to reject the null hypothesis. It's perfectly plausible that we could observe this difference in test scores if the null hypothesis is true, that the difference between reading and writing test scores really is 0. One final conceptual question on this topic. If we were to construct a 95% confidence interval for this average difference between reading and writing scores, would we expect that confidence interval to include 0, to overlap 0? Take a minute and see what you think. So yes, this interval should include 0, and we can double check that by calculating the confidence interval. We would take our point estimate, negative 0.545, plus or minus our margin of error, which we're going to calculate as the critical value for the 95% confidence interval, so 1.96, times the standard error. So that gives us a confidence interval of negative 0.545 plus or minus the margin of error of 1.23, an interval of negative 1.775 to positive 0.685. So that interval does contain 0, it does overlap 0. So why is that important? Well, remember that the 95% confidence interval sort of gives us our plausible bounds of what the actual value in the population could be. So our best guess is that the actual value lies somewhere between this lower bound and this upper bound. So with 95% confidence, the smallest we think this effect could be is negative 1.775, and the biggest we think it could be is 0.685. So those are sort of the limits on what we think this difference could actually look like in the population. So if that 95% confidence interval doesn't overlap 0, then we have a good idea of the direction of the effect. So if our 95% confidence interval has a lower bound and an upper bound that are both positive, that means that with 95% confidence, we're sure that there's a positive value for this difference variable in the population, which would mean that we're sure that reading scores are higher than writing scores, right, with this reasonable level of confidence. If our 95% confidence interval has lower and upper bounds that are both less than 0, that means that we're pretty sure that writing scores are greater than reading scores. And so the 95% confidence interval contains all negative values. When the 95% confidence interval overlaps 0, that means that within those confidence bounds, we don't even have any idea what the sign on that difference is, whether the difference would be positive or negative in the population. And so our best guess is that there isn't a difference, it's just 0. So that's been our lecture on paired data. The procedure for analyzing paired data is pretty simple. It's very similar to the procedure that we've been following doing hypothesis tests up to this point. In the next couple of lectures, we're going to get a little bit more complicated. Thank you for tuning in, and I'll see you next time.